Welcome to another exciting installment of Advanced Analytics. First and foremost, I would like to thank our sponsors for making this video possible, including but not limited to Azantec, Ryber Labs, the Fillmore Center for Extended Computing, GigaNet, the NASA Gamma Fusion Subcommittee, Rychten Enterprise Solutions, the Galileo Institute, and the Delta Machine Association. In our last video, we were discussing certain problem areas involving the di-polymer effect of Rychten forces on a non-malleable isomorph. We concluded by pointing out potential flaws in the gateway manifold and the resulting sectionalities that would need to be addressed in order to remedy the issues we were encountering. On this episode of Advanced Analytics, I'd like to go a little more into detail on some of those remedies, in particular the climittal ajoinment of the four sectors, the dark field solution, non-singular mapping, as well as the most trivial solution, which we all know to be the longeification of the Baxter-Brentworthy network. I'm sure you all are already well enough aware of the fundamentals of climittal ajoinment, so I'm just going to get right into it. What research uncovered was that this particular subfield of dissymmetric ajoinment was completely unbifurcated by not only the two main nuclear forces, but also by Wachsner's axionomic force, which until 2014 was thought to be present in all three-dimensional non-tangential planes. In layman's terms, under the right conditions, this solution could be extended to the Rychten forces as long as laterality was maintained on the plane. However, there are still several force sectors that would further fragment due to the volatile nature of doing anything climittal on such a large scale. Fortunately for us, you've probably already realized why those don't matter. If you haven't, remember, fragmentation has a definite solution as long as the lateral effect of the Rychten forces is less than 1 millitude of the original. So, we can escape bifurcation and the Rychten forces entirely if and only if all resulting fragmentation from the ajoinment in question has a tangible solution. Moving right along, let's get into some actual numerical analyses with the dark field solution. The dark field solution, as you all know, was originally designed to be the bridge between dipolymeristic bonds within an isomorphic special array and its free fixed components of the Baxter-Brentworthy dissociologic structure. It does this using non-asymptotic asymmetries of high-frequency anionic electromagnetic waves. Now, where does this come into play for our Rychten forces on a non-malleable isomorph? Well, the way the dark force problem works is that it uses subquantum, non-tangible eigenrefractors to circumvent the need for the required beta structures due to its dissociologic nature. At a limited scope research study conducted by the London Center for High Phase Molecular Computing, it was found that while bilateral refraction only had a reliable 15% success rate at maintaining the stability of a polymolecular compound held together with dipolymeristic bonds and being forced into a free fixed dissociologic state. However, when they tried the dark force solution, this percentage skyrocketed to around 71% average success rate, obliterating what was thought to originally be a 20% limit. Many Rychten theorists believe that even as high as 71% is, this number only seeks to increase when tested in a facility with higher phase semi-synchronistic polymeristic scrubbers. Although it is now believed that the dark force solution has a theoretical 100% success rate, what the research team found and a problem for future discussion were recurring anomalies recorded at the following three-dimensional tripolar space coordinates: 3.2%, 12 microns, 37 degrees, 7.4%, 108 microns, 90.1 degrees, and lastly an endpoint anomaly at 155 degrees, 41 microns, and 364.9%. Although there were thousands of other anomalies, these in particular increased the overall beta of the error by a whopping 16%. When asked what inside the project lead at the London Center for High-Phase Molecular Computing had to offer, he stated that despite the phenomenal results of the dark force solution, he found the clustered anomalies to be baffling, but expected the solution to become apparent within the next 5 years through continued research in quantum number theory. Moving right along to our next solution is the non-singular mapping. So, how can a basic non-singular mapping address sectionalities from the gateway manifold? Well, it turns out we actually need to use a pretty complicated non-singular mapping, commonly referred to in the field as a non-binary stack-turning map. While similar maps have non-lateral ordinality, in the stack-turning map we have the option to use lateral ordinality, which is why mathematicians, physicists, and computer scientists alike were elated when this was first proven to even be possible. It's very similar to the dark force solution. We have a valid proof that there does exist at least one polyrhythmic non-singular mapping that addresses the sectionalities of the gateway manifold that would either bypass or solve the di-polymer effect we were encountering. But as of now, all we know is that the solution exists. So far, there have been around 417 proposals with potential solutions, all with varying degrees of sophisticality, but none of them have the fuller unidimensional scope that would need to be applied to the non-malleable isomorphs. However, at the rate current progress is going, we can probably expect to see at least a theoretical solution within the next 16 to 17 years. I'd like to wrap up this episode by addressing the trivial solution, which is the longeification of the Baxter-Brentworthy network. As you all know, the reason this is the trivial solution is because it's already been proven to work, and by definition is a solution to our issue. However, the implementation of the electromagnetic containment housing, as well as the malleable variable nodes required to deal with our rychten-forces in question, would require an incredibly significant cost, as well as a sizable electrostatic field generator and inductor. And that's what makes this particular solution currently unfeasible. The lead chair on the project at Brentworthy Labs estimates that the current cost of implementing the solution would be around $91 trillion and would require an energy density of about 41 million terajoules per cubic millimeter per second, which is the equivalent of 41 quintillion lightning strikes per second, all directed at a micro-torsion-sized transistor. And if you have a standard-sized Maxwell containment unit filled to the brim with those transistors. Now, that's a lot of energy to provide at the moment, even for a lab as big as Brentworthy. But similar to the non-singular mapping solution, Brentworthy Labs have estimated to be able to devise a solution within the next several years, which would log-normally optimize it so that it could be implemented at only a fraction of the cost and energy input as what's anticipated now. On the next episode of Advanced Analytics, we're going to dive even further into the actual implementation of the longeification of the Baxter-Brentworthy network and do a full-scale analysis of the algorithms involved that would need to be used to optimize both the cost and electromagnetic efficiency of the solution. Thanks again for tuning in, and I will see you next time.